Problem 1. U is the natural numbers up to 6. A is the primes up to 5. B is the even numbers up to 6. And C is a minus B. We'll find a complement. Prove an identity about union and difference. And prove a Cartesian product identity. First, U, the natural numbers up to 6. Listing them gives 1, 2, 3, 4, 5, 6. Now A, primes up to 5. Testing each candidate 1 is not prime, since it has only one divisor. 2 is prime. 3 is prime. 4 equals 2 times 2. So it's composite. And 5 is prime. Also, 6 equals 2 times 3. So it's composite. That leaves or equals 2, 3, 5. Next, B. Even numbers up to 6. Checking 1 through 6, the even ones are 2, 4, and 6. Finally, C equals A minus B. Take A, which is 2, 3, 5, and remove any element that's also in B. 2 is in B, so it's removed. 3 and 5 are not in B, so they stay. That leaves C equals 3, 5. A complement is everything in U that is not in A, or occupies the regions labeled 2 and 3, 5, so the complement is 1, 4, and 6. The left-hand side, a union B, is every region touching either circle, 2, 3, 4, 5, 6. Now the right-hand side, step by step. A minus B is the part of A outside B3 and 5. B minus A is the part of B outside A4 and 6. And A intersection B is just the overlap 2. Combining all three pieces covers exactly the same regions as a union B2, 3, 4, 5, 6. The identity holds. First, or intersection C. Since C is 3 and 5, and both are already in A, or intersection C is just C3 and 5. So the left-hand side, or intersection C, cross B, pairs 3 and 5 with every element of B. Now the right-hand side. Across B pairs every element of A with every element of B, 9 pairs in total. C cross B pairs 3 and 5 with every element of B, 6 pairs. Intersecting across B with C cross B keeps only the pairs common to both, and that's exactly the same 6 pairs as C cross B. Since C is a subset of A, this matches the left-hand side exactly. The identity is confirmed. Here's a recap. A complement is 1, 4, 6. The union and difference identity checks out on both sides. And the Cartesian product identity checks out too. All three results confirmed. Thanks in advance for watching next part. Problem 2. Or equals R, B. X and B equals C, Y. Both subsets of U equals R, B, C, X, Y, Z. In part A will verify 3 relationships involving complements. In part B will find A intersection B. Union with A intersection B complement. We'll use one Venn diagram throughout. And re-shade it at every step. Here's the Venn diagram we'll use throughout. Circle A on the left. Circle B on the right. Both inside the rectangle for U. A, B, and X sit inside circle A only. Since A and B share no elements, the overlapping lens stays empty. C and Y sit inside circle B only, and Z sits outside both circles, but still inside U. First, B complement. Everything inside U that's outside circle B. That's the A-only region together with Z, and we shade the whole of that outside area in a single color. Now look at circle A. Its elements, A, B, and X, all sit inside circle A, which lies entirely within the shaded region. So every element of A is also in B complement, meaning A is a subset of B complement. Circle A on its own, A, B, X, and B complement, shaded as one color again, the A-only region plus Z. Taking their union covers exactly the same shaded area as B complement alone. Nothing new gets added, because A was already inside B complement. So a union B complement equals B complement. A complement. Everything outside circle A, shaded as one color, the B-only region together with Z. And circle B on its own, C and Y. Intersecting a complement with B keeps only what's common to both shaded regions, circle B itself, since B lies entirely inside a complement to begin with. So a complement intersected with B equals B. A intersection B is the overlapping lens in the middle of the diagram. A and B share no elements, so that lens is empty. B complement, shaded as one color, everything outside circle B, the A-only region, plus Z. A intersection B complement is the part of circle A that also lies in B complement, exactly the A-only region, since the empty lens isn't part of B complement. That's a B, X, which is just A. Combining step 1 and step 3, the empty lens together with the A-only region, covers exactly circle A, B, X. So A intersection B, union with A intersection B complement, equals A. This is a general identity. It holds for any two sets A and B, not just this example. So the answer is A, B, X. Let's show that two subsets of the universal set U, containing the numbers 0 through 9, really are subsets. Using a Venn diagram, set A is the set of prime numbers in U, and set B is the set of odd numbers in U. Recall that a set is a subset of U if every one of its elements is also an element of U. Checking each number from 0 to 9, the primes are 2, 3, 5, and 7, so A equals 2, 3, 5, 7. The odd numbers are 1, 3, 5, 7, and 9, so B equals 1, 3, 5, 7, 9. Notice A and B share three numbers 3, 5, and 7 which are both prime and odd. Here's our Venn diagram. Circle A on the left, circle B on the right, both drawn entirely inside the rectangle representing U. 2 goes in A only. 1 and 9 go in B only. 3, 5, and 7 sit in the overlap, since they belong to both sets. And 0, 4, 6, and 8 sit outside both circles, but still inside U. First, is A a subset of U? Circle A is drawn entirely inside the rectangle for U. Every point in circle A, including the overlap it shares with B, sits inside that boundary, checking each element. 2 is in U. 3 is in U. 5 is in U. 7 is in U. Every element of A is in U. So A is a subset of U. Next, is B a subset of U? The same reasoning applies. Circle B is drawn entirely inside the rectangle for U. Checking each element. 1 is in U. 3 is in U. 5 is in U. 7 is in U. And 9 is in U. Every element of B is in U. So B is a subset of U. So both A and B are subsets of U. Notice the purple overlap 3, 5, and 7, which are prime and odd at once. That region still sits fully inside U2. Since both circles were drawn entirely within the boundary of U from the start, neither set could ever contain an element outside it. That's exactly what it means to be a subset. Thanks for watching.